Good day. So in the last class we discussed about TTT diagram. So here this graph showing the transformation of oscillate with respect to temperature. Here at this point we have 100% oscillate, and here at this point when the time progress at 10 to 2 seconds, and the 50% of oscillate is converted to palate, and remaining 50% is converted into palate, and this point corresponding to 0% oscillate and 100% palate. Okay, so corresponding to these 3 points, we can draw 3 points in this graph, temperature time graph. And this point is the 100% or starting of oscillate conversion point, and this point, center point, is the 50% oscillate conversion point, and the last point, the green color point, that is the 0% oscillate or entirely oscillate is converted into palate. Okay, and similarly we can draw a number of such horizontal lines. So here we can see, so this is the horizontal line for this 100% oscillate and 0% oscillate, and similarly we can draw such a number of horizontal lines. For example, in this case, here we have different temperature. This is the oscillate transformation for 550 degrees Celsius. This is for 400 degrees Celsius, and this is for 650, and this is for 250 degrees Celsius. And this graph is the output from different types of experiment. Okay, so we take a sample and we dip that sample. First we heat the sample above oscillate temperature. Then we dip that sample, which is dip that sample in a salt bath or any cooling medium, which is maintained at 550 degrees Celsius. Okay, so what happened? The oscillate starts to convert from oscillate state to any other microconstituent state, and at this point, entire oscillate is converted to another microconstituent. Okay, so if you take the 250 degrees Celsius, so this is the starting point. I can draw a vertical from the starting point, and corresponding to 250, I can draw a line here also. So we got a point here. Okay, similarly, see this for B2, this line, that is 0 time and 0 degrees Celsius. B2, sorry, it's not 0 degrees Celsius, it is B2, that is at 550 degrees Celsius. Okay, B2 at a starting point of oscillate, or 100% oscillate is here at B2 at 550 degrees Celsius. So I can draw a vertical line. So here also I can draw a 550 degrees Celsius horizontal line. So these two lines meet at this point, that is B2. Similarly, the 100% oscillate is converted to another constituent. Again, I draw a vertical line. That means this horizontal line at this point E2. So I got a horizontal line here. So I got a horizontal line here connecting B2 and E2. Okay. Similarly, I can draw another curve. Another curve that is for 650 degrees Celsius. Okay, this is the transformation of 660 oscillate at 650 degrees Celsius of salt bath. Okay, so here at this point we have 100% oscillate. At this point, the entire oscillate is converted to another microconstituent. Okay, so when we draw a vertical line that meet a horizontal line that is at 650 degrees Celsius, we got these 2 points B1 and E1. Okay, so again I can draw a horizontal line here. Okay, and similarly again another curve with 400 degrees Celsius. Draw 2 vertical line. Again draw a horizontal line in this corresponding to 400 degrees Celsius. We got 2 points, and draw a horizontal line here. Okay, then again for this 250 degrees Celsius, we got this 2 green vertical line. Corresponding points also can be marked with the with a horizontal line. Okay, so here we got different horizontal lines. Okay, different horizontal lines. So we got different horizontal lines. by connecting all the horizontal lines, we get this TTT diagram. Okay, by connecting all, similarly, we can draw a number of horizontal lines by connecting these horizontal lines. Starting point of the horizontal lines, we got this curve, and by connecting all the ending points of the horizontal line, we got this ending curve. Okay, so oscillate enter this pink color curve, C curve. This is called C curve. In this pink color C curve, we can say oscillate percentage is 100%. Okay, and when the C curve shifted to the right, okay, the oscillate percentage is reduced from 100%. Some of the oscillate is converted to another micro constituent. Okay, and at this green curve, green C curve, the entire oscillate is converted to another micro constituent. Okay, so these are the C curve. This is called C curve, and this curve is called S curve. Okay, we can see the shape. It is like an S, and it is like a C. So we got two C curves, and here we got a S curve. And when we compare the different micro constituents, what are the different micro constituents form? In this, we have different zone. We can divide this into different zones based on this nose area. This point is called nose area. This area is called nose area. This one, this area. Because here we can see this is the area where the oscillate is rapidly converted to another micro constituent. Okay, in the nose area, we can see the 100% oscillate is suddenly or with a very high rate converted to 0% oscillate. Okay, what is the reason? Here we can see when we draw a vertical line between these 2 points, it is starting at less than 10 seconds and it is ending before 100 seconds. Okay, but if you take another point, you can take another point in the same straight line, sorry, in the same curve. This is above 100 and that is 500. For example, this is 500 seconds and this is equal to 10 raised to 3 is maybe 5,000 seconds. So there is a big gap between these two lines, 2 points. High time is required for the conversion of 100% oscillates to 0% oscillate in this point. But here, when we take these 2 points, we can say with a very small amount of time, the entire oscillate is converted to another micro constituent. So this point, this area is called nose area of the C curve. Nose area of the C curve. And in this nose area, we have very high rate of oscillate conversion. Okay, that is why it is called nose area. So in the upper side of this nose area, we can say the entire microstructure developed in the upper side of this nose area is called palate. The palate is formed. Okay. In the bottom side of this nose area, the microstructure is formed called bayonet. So in this area, we got bayonet. Okay. And below this bayonet line, we got martensite. Okay. So these are the 3 micro constituents formed in the TTT diagram of eutectoid steel. This is very important. It is formed for eutectoid steel. So here we use the composition of eutectoid steel, that is 0.76% of carbon. Okay, so we can divide the micro constituent, the oscillate, 100% oscillate. At this point, we have 100% oscillate, and this 100% oscillate suddenly cooled to a 650 or 400 or 200 degrees Celsius, and then we isothermally cooled in the salt bath. Okay, and in this point the oscillate is 100%. That means here we have a stable oscillate above 723 degrees Celsius. Okay, the stable oscillate, when we rapidly cool, at this point we got unstable oscillate. But this unstable oscillate start converting only at this point. Okay, the unstable oscillate start to convert into another constituent at this point, the starting point of this curve. And the conversion happened here. 100% oscillate slowly converted into 0% oscillate. and the austenite in this region is converted into palate. And here in this region, the austenite is converted to bainite, and in this region, the austenite is converted to martensite. Okay, this is the explanation of TTT diagram. Any doubt in this area? So three micro constituents are formed: palate, bainite, and martensite. Okay. So at the high cooling rate, this is in this region. This is the high cooling rate region. Low cooling rate. We got palate. This is the low cooling rate because here we only cool from in this region. If you take this region, we cool from 723 to maybe higher than 50 degrees Celsius. So the temperature gap is very small compared to this bayonet region. We only cool from 723 to 650 or above 550 degrees Celsius. So the delta T is very small compared to other region. So we can say the cooling rate is low when we convert austenite in this region. So when the cooling rate is small, the resulting microstructure is palate. Okay, but here we can see in this region, that is the bayonet formation region. In the bayonet formation region, we cool from 723 to around above 300 degrees Celsius. So the cooling rate is high. We suddenly decrease the temperature from 723 to around 300. Okay, the decrease in temperature is very high, or delta T is very high. So if the cooling rate is very high, then corresponding microstructure formed is bayonet. Okay, and here the third case, we cool from 723 to very small temperature above 250 degrees Celsius, about 250 degrees Celsius. So the cooling rate is very high. Okay, suddenly we decrease the temperature of the sample, austenite sample, from 723 to around 100 or room temperature or 200 degrees Celsius. So the temperature gap is very high, or delta T is very high, cooling rate is high, then the resulting solid is equal to, or microstructure is equal to, martensite. Okay. So the size of the palate and bayonet depend upon the transformation temperature. Okay. And martensite form when the steel is cooled below martensite start, MS. We can see MS horizontal line. So we have to cool below this MS line, then only martensite starts to form. Okay. And with a much higher cooling rate, we have to dip this 723 above 723 degrees Celsius austenite into very cold medium. It may be oil or it may be water, which is at the room temperature. We got martensite structure. Okay, and the diffusion rate in the austenite to martensite transformation is very less, or we can say it is a diffusionless process. I will explain that later. And we got a body-centered tetragonal shape microstructure, crystal structure for a martensite. Okay, for the martensite, this is the microstructure, crystal structure BCT, body-centered tetragonal. I will explain these 2 points later. So next I am going to explain different micro constituents. Okay. So what are the structures of different micro constituents? That is, first one is palate, and the second one is bayonet, and third one is martensite. Okay. Next I am going to explain these 3 micro constituents. First one is palate is formed at a very high temperature range. Okay. So here in this TTT diagram, So here in this TTT diagram, this is temperature, this is time in logarithmic scale. Okay, so this is 723 degrees Celsius. 723 degrees Celsius. Okay, and this is the corresponding.
Sir. Sir, 727 ആണോ 723 ആണോ?
range 727.
Okay.
Callister next is 727. Okay. So this is a TTT diagram. Okay. And here this is the nose area. Nose area. Above the nose area we got paleite. So this region will be paleite. Paleite is formed. Okay. And in this region we know the temperature is very high. Okay, compared to this region, the temperature is high. So in paleite formation, the temperature is very high. Okay, for the paleite formation, the temperature is very high, just below the eutectode temperature. And the paleite region again can be divided into two. Paleite region again can be divided into two. So this is divided into two. Okay, so this region is called coarse paleite region, and this region is called fine paleite region. Fine paleite region. Okay, and this paleite, what is the composition of paleite? Paleite composition is nothing but alpha plus Fe3C, what we studied in the iron carbon equilibrium diagram. Okay, there is no change in that. The composition is same. When we cool from austenite state to the this crossing the eutectode point, we got alpha plus Fe3C. So the composition is alpha plus Fe3C, but the structure, when we look through a microscope, it's like structure is like plate-like structure, what we studied in the phase diagram, iron carbon equilibrium diagram. So how this paleite is formed? There will be an alternative layer of alpha and Fe3C, right? This will be Fe3C, and the intermediate region is alpha. So a plate-like structure or laminar structure or structure is formed for a paleite. And when we compare the relative thickness of the alpha and this Fe3C, in coarse paleite, the thickness will be very high. Okay, the thickness of these plates will be very large for a coarse paleite. What is the reason for that? So here we can see from the austenite temperature, we only heat to very small temperature, means we heat to very high temperature. Okay, then we isothermally cool into cool the austenite, and the resulting solid is the coarse paleite. So here we can see the cooling process happening at a very high temperature compared to the martensite and bainite. Compared to martensite and bainite, this for the coarse paleite, the cooling temperature is very high. So if the temperature is very high, the formation of nucleus also will be very small. Very small number of nucleus, or minimum number of nucleus will be formed at high temperature, because there is no driving force for the formation of nucleus at a high temperature. So small amount of nucleus will be formed, as well as the growth rate of the nucleus is very high. So nucleus suddenly starts to grow. Okay, so at high temperature, nucleation rate is small, but the growth rate of the nucleus is very high. So number of grains formed in this region will be very small, and the size of the grain is very high, very large. Okay, so the size of the grains will be very large, and the number of grains formation will be very less. Okay, so that is the reason for the coarse paleite structure in this region. But if we consider this region where we got fine paleite, and in case of fine paleite, we can say that we initially reduce the temperature to this value, which is almost which is in the middle range of temperature. Then we isothermally cool into cool in a salt bath. Okay, so here 100% austenite is converted to fine paleite. Okay, so in this range, what happened? We have a microstructure like this. The size of the intermediate layers of Fe3C and alpha will be very small. Okay, a very small size is formed. That is, fine size of plate is formed in the cross section of the fine paleite. Okay, so but here it is a coarse plate arrangement. We can see a coarse plate arrangement, but here we can see a fine plates arrangement of alpha and Fe3C. What is the reason for that? Here we can say compared to coarse plate, here we have low temperature. At a low temperature, the number of nucleus formation will be high. Okay, large number of nucleus will be formed at a low temperature. Okay, and this nucleus starts to grow in different points, different number of nucleus is formed. So the growth rate will be small because here we have different nucleus and each nucleus growth restrict the growth of another nucleus. So thereby the growth rate will be small. So we have number of such nucleus is formed, number of such grains will be formed. Okay, so each grain size will be small. The resulting solid will be a fine grained structure. So we got coarse pellite and a fine pellite. Okay, so coarse pellite and so relatively thick layers of alpha and Fe3C form in the upper region of the pellite, and high temperature, high diffusion rate allow large grain growth. Okay, in this region we have large grain growth, but the nucleus form will be less. Number of nucleus formed is very less. Okay, so that is the reason for this coarse pellite formation. And with the decrease in temperature, carbon diffusion rate decreases. And layers become progressively thinner. Okay, അപ്പോൾ solid formation അല്ലെങ്കിൽ ആ diffusion rate decrease ചെയ്യും, ഈ carbon diffuse ചെയ്തിട്ട് rate reduce ചെയ്യും, അതുകൊണ്ട് തന്നെ ഈ fine ആയിട്ടുള്ള pellets ആയിരിക്കും form ചെയ്യും. Okay, and we can see the fine layered pellite structure at the vicinity of 540 degrees Celsius. So this is the pellite structure, alternative layers of alpha ferrite and Fe3C cementate is formed for the pellite structure. Okay, coarse pellite and fine pellite are formed. So this is 727 degrees Celsius to immediately be sconged. The sconging means we dip a particular material in a very small temperature. That is sconging. The rate of cooling is very high for sconging operation. Okay, sconging operation. So here we can see we reduce the temperature immediately, suddenly from 727 to this 650 degrees Celsius. So this process is sconging, AB. Then we isothermally cool that medium. The resulting solid is coarse pellite. So this is the comparison of coarse and fine pellite, and this is the fine coarse pellite. This one is coarse pellite, and this one is a fine pellite under the microscope. And the second component is bayonet. Okay, another microstructure which is formed from TTT diagram is called bayonet, and the reason for this bayonet, the name is for honoring a scientist called Edgar C. Bain, who developed this TTT diagram. Edgar C. Bain developed this TTT diagram. So to honor this Edgar C. Bain metallurgist, we use the name of his name for bayonet. Okay, bayonet. His last name Bain is used for naming this microconstituent bayonet. Okay, and where this bayonet form? Bayonet is formed below this nose area of the TTT diagram. So this area, in this area we develop bayonet. Okay, so when we cool the austenite sample below this nose area temperature, we got bayonet. Okay, so in addition to bayonet, two other microconstituents that is product of the austenite transformation exist, that is called bayonet. The microstructure of bayonet consists of ferrite and cementate. There is no difference in the microconstituents. Okay, there is no difference. Here also we have alpha and Fe3 space similar to pellite. But what is the difference between pellite and bayonet? That is only the difference in shape and the phase difference. The shape difference. Okay, the microconstituent shape is different. What is the difference in shape between pellite and bayonet? In case of bayonet, a needle-like or plate-like structure can be seen under microscope. Okay, under the microscope, a needle-like or plate-like structure we can see for a bayonet. But in case of Payload, we can see a plate-like structure with a thick plate. Here we have a thick plate. Even for a coarse as well as fine plate payload, we have thick plate of Fe3C and ferrite. But here we can see very small size plates for bayonet. Very small, like a needle. Okay, like a needle. So that is the main difference between payload and bayonet. There is no difference in the composition of the phases, both made with the alpha ferrite and Fe3C cementate. But the difference is in the structure. When we look through a microscope, we can distinguish this payload and bayonet. Okay, so that is at below that of payload forms. Okay, so this is the bayonet formation. We rapidly cool to, for example, this is an example. This is not the exact temperature. Below this this nose area, we can see this is a nose area. Okay, so below this nose area, we can produce bayonet. Okay, so we can cool to any temperature. Here I am cooling to this 350 degrees Celsius rapidly by dipping into a salt bath. Then I maintain that same temperature in the salt bath. And here at this point, the bayonet, at this point, the bayonet 100% austenate, and austenate slowly converted into bayonet. And at this point, entire austenate is converted to bayonet at this ending point. Okay, and here we can see entire bayonet material. Okay. So this is bayonet. And the process which is used for producing bayonet is called Ostempering. Ostempering is the process. We will study the process later. So Ostempering is used to produce bayonet. Okay. So this is the microstructure of bayonet, and this is martensite. We will explain what is martensite later. And here in this bayonet, we can see this is cementate. The cementate present in bayonet. Okay. Bayonet is made with the alpha ferrite and Fe3C cementate. Okay, and how this alpha and Fe3C are arranged in a bayonet? Here we can see the ferrite and cementate. Okay, so this is a microscopic picture from a electron microscope. So here in this needle-shaped particles, so Fe3C within the ferrite matrix. So Fe3 is like a needle shape. You can see a needle-shaped particles of Fe3C you can see in the case of bayonet. But if it is a payload, the thickness of the cementate will be more. It may be like this. Thickness will be higher. But in this case, for bayonet, this thickness is very small. It is like a needle. It is like a needle, which is embedded in the ferrite matrix. Okay. So here, this is the C-shaped curve. We have nose area that is at this point N. It is around 550 degrees Celsius, 540 degrees Celsius. And here in the nose area, the rate of transmission is maximum. Suddenly, the 100% austenate converted to 0% austenate. Okay, the rate of transmission compared to all other regions in the TTT diagram, here we have high rate of transmission. So this is very important. Phases versus microconstituents. Okay, in case of bayonet as well as payload, both constitute two mixtures, that alpha plus Fe3C. There is no change in the phases. Both constitute alpha plus Fe3C. But what is the difference between payload and bayonet? That is only the difference in the shape. Both have different shape. For payload, we have a plate-like structure, a thick plate-like structure of ferrite and cementate can see in the payload. But what is the shape of this bayonet? We can see needle-like shape of the cementate in bayonet. So that difference in shape is actually distinguish this bayonet and the payload. And another factor is the distribution of the space. Okay, that maybe the phases may be uniformly distributed in one case, and in another case the phases may be segregated to other regions. Okay, so distribution may be different. So depending upon the different shape and distribution, we give different name for this same phase. Alpha plus Fe3C, we give different name for this two micro constituents. Okay, so here micro phases are same, but micro constituents are different for bainite and palate. And the last one is martensite is formed. Martensite formation is in this region. We cool from the austenite temperature. Suddenly, we cool from austenite temperature suddenly. And at this point, what happened? The martensite is start, and again by quenching the martensite, entire austenite is converted to martensite. So here at this point we have unstable austenite. At this point we have unstable austenite. At this point we have unstable austenite, and when it progresses through this line, the entire austenite is converted to martensite. Okay, so that is the martensite formation. And here in this is very important. In this martensite formation, this line does not touch this TTT diagram. We can see this is not touching in this TTT diagram. This line. That means that actually this TTT diagram gives a relationship between the temperature and time. Okay, this TTT diagram gives the relationship between temperature and time. Okay, but this martensite line does not touch, not touching this TTT diagram. That means this martensite formation is independent of the time. There is no relationship between time and the martensite formation. Martensite formation is purely dependent upon the temperature. Okay, from what temperature to what temperature? From what temperature to what temperature we cool the material. Okay, or the rate of cooling. The rate of cooling is the main factor affecting the formation of martensite. Okay, the time is irrelevant in the case of martensite formation. That is why this martensite formation is not touching this TTT diagram. Okay, it is not touching the TTT diagram. And this process, the martensite, for example, the formation of martensite, what we do, we take a beaker and it is full of water or oil that is at a room temperature, and we heat the specimen into austenite temperature. So entire above austenite temperature, entire microstructure changes to austenite, and we suddenly dip the austenite sample into this water at a room temperature. So here the temperature is above 727 degrees Celsius, 727 degrees Celsius, and here the temperature may be 10 degrees Celsius. Okay, so we can see the difference in temperature compared to palate and bainite. Here the temperature difference is very high. Okay, so from 727 degrees Celsius to 10 degrees Celsius, a rapid cooling will occur. Because of this very rapid cooling, or the cooling rate is very high in case of martensite, what happened? There is no time available for the diffusion of the particles. Okay, there is no time available for the diffusion of the particle. How the diffusion happen? See this. In this, we have in gamma. In gamma, we have that is FCC crystal structure. FCC crystal structure. The iron particles are there, and interstitial carbon particles are there in gamma state. Okay, that is above 727 degrees Celsius. We suddenly cool this into 10 degrees Celsius. Here it is 727 degrees Celsius. Gamma particles is with FCC crystal structure. We suddenly cool into 10 degrees Celsius. Okay, 10 degrees Celsius. So actually, in the two palate and bainite formation, what happened? In case of palate and bainite formation, this gamma converted into alpha plus Fe3C, right? For palate as well as bainite, gamma is converted to alpha plus Fe3C. So for example, in case of gamma, we have 2.14% of carbon. Alpha, we have 0.02% of carbon. And Fe3C, we have 6.67% of carbon. Okay, so that means in palate and bainite formation, the interstitial carbon atoms come out from the gamma substance. Okay, during this transformation, during the palate and bainite formation, when we convert austenate, 100% austenate into alpha plus Fe3C, what happened? This interstitial carbon atom from the gamma austenate is come out from the structure, and this carbon atom react with the iron and form Fe3C. Okay, and the remaining parts, some of the carbon atom come out from the gamma austenate. So there will be a remaining structure that is with a less amount of carbon. So that is alpha. Okay, so this is alpha. This is alpha with a low amount of carbon, and the carbon atom come out from the austenate, react with the Fe3C and form 6.61% in the Fe3C. So this is actually happen in a bainite and a palate formation. So for this, we need a movement of carbon atom. Carbon atom has to move from the FCC crystal structure of gamma to outside. Okay, from the interstitial position, they have to diffuse. Okay, so the large rate of diffusion happened here in case of palate and bainite, and they got enough time for the diffusion. They got enough time for palate and bainite. They have enough time, but in case of martensite, the time is very low, because we know the martensite we cool from 727 to 10 degrees Celsius at a very small time. So this type of diffusion will not occur in case of martensite. Okay, this type of diffusion will not occur in the case of martensite. What is the reason? They don't get enough time for the diffusion. Okay, this transformation is very rapid, so they don't get enough time for the diffusion. So such type of carbon diffusion not occur in this case of martensite. Okay, so we can say this is the diffusionless transformation. There is no diffusion in case of martensite. So if there is no diffusion, that means when we cool gamma from 727 degrees Celsius to 10 degrees Celsius, the resulting solid also will be gamma. This also will be gamma, right? That means if there is no diffusion, if there is no atomic movement, then the final solid will be equal to the initial solid. But the final solid is not initial solid. What is the reason? When we cool from 727 degrees to 10 degrees Celsius, what happened is that the gamma, that is as FCC crystal structure, changes to another crystal structure. There is no diffusion here. There is no diffusion of carbon particles here, but the entire crystal structure of gamma, which is initially FCC, changes to another crystal structure that is called BCT, body cubic tetragonal crystal structure. Okay, so that is the difference between the gamma and the martensite. Okay, there is no diffusion, and here in this we don't have the alpha plus Fe3C. Okay, alpha plus Fe3C is not formed here. Here, the interstitial carbon atom without any diffusion converted to martensite. There is no phase change here for the martensite formation. That is why this martensite is not included in the phase diagram of fine carbon equilibrium diagram. Okay, this is not included because here there is no phase change. There, the phase is same, but what is the difference between the gamma and the martensite? The only difference is the crystal structure is changed from FCC to BCT. Okay. So in case of martensite, that is martensite rapidly cooled or quenched. The rapid cooling process, another name is called quenching process, and relatively to low temperature, it may be a room temperature, and a single phase structure. This is very important. There is no change in the phase during this transformation. So this is a non-equilibrium single phase structure that results from a diffusion-less transformation. This is very important. There is no diffusion happening in this case of martensite formation. But in case of palate and bainite, we have diffusion. But here we don't have any diffusion. So martensite transformation occurs when the quenching rate is rapid enough to prevent the carbon diffusion. There is no carbon diffusion in case of martensite formation. And how this martensite is formed? This is occurring in such a way that FCC austenite experience a polymorphic transformation to BCT martensite. So FCC changes to BCT. Entire crystal structure is changed. FCC changes to BCT. Okay. So all the carbon atom remain as in the interstitial impurity in martensite. As such, they are constitute a supersaturated solid solution. That is how body-centered tetragonal lattice. There is no change in the interstitial carbon atom that remain in the same state. But what is the change? The change in the entire crystal structure of the material, that FCC changes to BCT in case of martensite formation. Okay, so instead of diffusion, a sudden reorientation of carbon and iron atoms from the FCC solution austenates to a body-centered tetragonal solid solution happen in case of martensite formation. So diffusion less, reorientation of carbon and iron atom takes place during this transformation. There will be a reorientation. Okay, the crystal structure is changed by this reorientation. So FCC changes to BCT in case of martensite formation. So this is the martensite formation. It's an example. Here we hold at 100 degrees Celsius. We can hold at 100 degrees Celsius at this 250, or we can suddenly const into this martensite transformation. That means I can do like this also. I can do like this also. Okay, we don't need to maintain 100 degree, 100 second holding here. We can suddenly change to martensite. Okay, this is the martensite formation. So this is the BCT crystal structure, and in case of, we already studied FCC crystal structure. The only difference is that in the FCC crystal structure already we have in this gamma we have FCC crystal structure phase centered, and when rapid cooling happens, what happens? This FCC, the iron atoms present and the carbon atom present in the FCC crystal structure reorient. Okay, they change their position, but that change in position is maybe 1 atomic distance or 2 atomic distance. That we are not considered as a diffusion. But in case of this this diffusion, this may be more than 2 or 3 atomic distance. Okay, the carbon atom displaced by 2 or 3 or 4 atomic distance. But here this carbon as well as iron atom displaced by 1 atomic distance, and they reorient. And by the reorientation, the FCC changes to BCT. So this is a BCT crystal structure. What is the difference? Here all the blue colored one is iron atoms, and the dark color is carbon interstitial atom. And here the main difference is between BCC and BCT is that BCC means body-centered cubic. So in BCC we have cubic crystal structure. A and B and C are same, but here we have C with a higher value. Okay, A and B are same, but in case of BCT, A, B, and C value, that is height is greater than that of A and B. That is the difference between BCC and BCT. And martensite has very hard and brittle structure. So hardness is a very good property of the material, but this brittle nature of the martensite is a disadvantage for the engineering application. Okay, it is suddenly failed without any deformation. So that is a martensite structure. So martensite transformation, austenite is converted to martensite. Extremely rapid transformation is occurred in case of martensite, and this transformation is athermal transformation. That means the rate of transformation does not depend upon the temperature. Okay, that means there is no influence of time. Okay, there is no influence of time for this transformation. Okay, time is independent here, and it does not depend on the temperature. Time is independent of temperature in case of martensite transformation. And there is no change in the composition. Here, initially we have gamma composition, and finally also we have gamma composition. The phase does not vary. Okay, but in case of pyrite, we change from gamma to another 2 phase. But in case of martensite, the austenates remain as same phase, but the structure is changes from FCC to BCT. And this is a diffusionless transformation, martensite transformation. And this is the microstructure of martensite. It is like a needle-like structure. Okay, a needle-shaped structure we can see in case of martensite. Okay, so this is the different cooling process. Here we cool from 727 up to 650. Then we maintain isothermally at up to a particular time. At the end of time, we got only 50% austenite is converted to pallite. Okay. At that time, again I cool into 400 degrees Celsius. I reach this point. And again I isothermally cool at that temperature of 400 degrees Celsius, entire austenite is converted. What is the resulting solid? It will be 50% pallite, 50% bainite. Okay. And another cooling is this 727 degrees Celsius to 350 degrees Celsius. Isothermally, I cooled this material. Then rapid cooling to room temperature. So at this point, we got 100% bainite, but we have to cool into room temperature. That is this process. Okay, this process is cooling. So we got 100% bainite. And if we cool rapidly up to 250 degrees Celsius and maintain at a particular temperature, we got martensite. We don't need to maintain this temperature for case of martensite. We don't need to maintain this temperature. That means this horizontal line is not needed for here. We can either we can use or we can omit that. Okay, but here in this we need these horizontal lines because this is an isothermal process. Okay. And the last one is another material which is formed in the TTT diagram is spheroidite. Spheroidite. Okay, and the spheroidite is formed when we heat the pallite or bainite microstructure and to below the eutectonic temperature. It's not greater than eutectonic temperature, below the eutectonic temperature. That means 727 degrees Celsius. Okay, and we maintain at that temperature for a long time. Okay, below, for example, 700 degrees Celsius, we heat bainite and pallite up to 700 degrees Celsius, and then we maintain very long time at that temperature. That means 18 to 24 hours we maintain at that temperature. Then we get a microstructure which is called spheroidite. And we cannot see this spheroidite in the TTT diagram because this is an additional process. This is an additional process. So we got spheroidite. And what is the microstructure of spheroidite? In this spheroidite, we have in the alternate layers of ferrite and cementate can be seen in pallite. Okay, and as well as in bainite. Okay, alternate layers of cementate and ferrite like a plate we can see in pallite as well as bainite. But in case of spheroidite, we can see a spear-like structure of this Fe3C. Okay, plate-like structure is changes to spear-like structure when we maintain this pallite and bainite at below eutectonic temperature for a long time. This plate-like structure of the bainite and the pallite converted into spherical shaped structure. Okay, so this spherical shaped structure is a very ductile material compared to all other material, pallite, bainite, this martensite. This spheroidite is the very ductile in nature, but the strength is low, but which is very ductile in nature. This is because of the spherical shaped cementate, and this spherical shaped cementate has less ability to block the dislocation, thereby the this ductility of the material improve. So this is another material called spheroidite.
സാറേ അത് എങ്ങനെ ഉണ്ടാവുന്നതെന്ന് ഒന്നുകൂടെ പറയാമോ? അതിന് വ്യത്യാസമൊന്നും ഇല്ലല്ലോ പേളായിട്ടുമായിട്ട്?
The only difference is that in this spheroidite also we have alpha plus Fe3C. Alpha plus Fe3C. The micro constituents is there is no difference in the phase. Alpha plus Fe3C is formed, but the only difference is that the shape of the cementate. Okay. In case of pallite and bainite, we have a plate-like or needle-like structure. Okay, of cementate and ferrite. But here in this cementate has spherical shape. That is only difference. So when we maintain at this high temperature, 700 degree or below eutectonic temperature for a long time, the plate-like cementate converted to spear-like structure.
സാറേ അതിനാണ് കൺഫ്യൂഷൻ വരുന്നത്. അതായത് ആ ടെമ്പറേച്ചറിൽ കുറച്ചേരം ഇട്ട് കഴിയുമ്പോൾ അതെന്തായാലും 100% പേളൈറ്റ് ആയിട്ട് മാറുമല്ലോ.
100% ഓൾറെഡി പേലൈറ്റിനാണ് നമ്മൾ 700 ഡിഗ്രി സെൽഷ്യസിൽ കൊണ്ടുവരുന്നത്. ഇപ്പൊ എന്താ സംഭവിക്കുന്നതെന്ന് വെച്ച് കഴിഞ്ഞാൽ ഈ പേലൈറ്റ് നമ്മൾ 700 ഡിഗ്രി ഹൈ ടെമ്പറേച്ചറിൽ ഈ ലോങ് ടൈം വെക്കുമ്പോൾ പ്രോപ്പർ ആയിട്ടുള്ള ഡിഫ്യൂഷൻ നടക്കും. 100% ഡിഫ്യൂഷൻ നടക്കും. ഇനഫ് ടൈം ഉണ്ടായിരുന്നു ഡിഫ്യൂഷൻ നടക്കാൻ. അങ്ങനെ ഡിഫ്യൂഷൻ നടന്ന് എന്ത് ചെയ്യും, ഈ ഹൈ ടെമ്പറേച്ചറിൽ നമ്പർ ഓഫ് ന്യൂക്ലിയസുകൾ ഫോം ചെയ്യും. കുറെ ന്യൂക്ലിയസ് ഫോം ചെയ്ത് ഓരോ ന്യൂക്ലിയസും ഗ്രോ ചെയ്ത് ഓരോ സിമെന്റേറ്റ് പാർട്ടിക്കിൾസ് ആവും. അപ്പോ ഈ പ്ലേറ്റ് ലൈക്ക് സ്ട്രക്ചർ മാറിയിട്ട് സ്പിയർ ലൈക്ക് സ്ട്രക്ചർ ആയിട്ട് മാറും. നമ്പർ ഓഫ് സച്ച് സ്പിയർ ലൈക്ക് സ്ട്രക്ചേഴ്സ് ഫോം ചെയ്യും.
അല്ല സാറേ, അപ്പം യൂട്ടക്ടോഡ് ടെമ്പറേച്ചർ അല്ലേ 700 അല്ലല്ലോ. 700 എന്ന് പറയുമ്പോൾ
യൂട്ടക്ടോഡ് ടെമ്പറേച്ചർ താഴെ, ബിലോ യൂട്ടക്ടോഡ് ടെമ്പറേച്ചർ. ദാറ്റ് മീൻസ് 727 താഴെ ആവണം ഹീറ്റ് ചെയ്യേണ്ടത്. മുകളിലായി കഴിഞ്ഞാൽ ഓസ്നേറ്റ് ആയിട്ട് കൺവേർട്ട് ആവും.
അതാ അപ്പം 727 താഴെ അപ്പം പേളൈറ്റ് തന്നെ ആണല്ലോ.
പേലൈറ്റ് ആണ്, പക്ഷെ ആ പേലൈറ്റ് 727 ഡിഗ്രി സെൽഷ്യസിൽ നമ്മൾ ലോങ് ടൈം വെക്കുകയാണല്ലോ. പേലൈറ്റ് എന്ന് പറയുന്നത് നമ്മൾ എപ്പോഴും എന്ത് ചെയ്യണം, ഇതുപോലെ ഈ പേലൈറ്റ് കൺവേർട്ട് ആയി കഴിഞ്ഞാൽ നമ്മൾ അപ്പൊ തന്നെ റൂം ടെമ്പറേച്ചർ ഇട്ട് കൊണ്ടുവന്നോളാം. എങ്കിലേ പേലൈറ്റ് ആയിട്ട് മെയിൻറ്റെയിൻ ചെയ്തോളൂ. ഓക്കെ, ഈ ടെമ്പറേച്ചർ തന്നെ ലോങ് ടൈം വെച്ച് കഴിഞ്ഞാൽ പേലൈറ്റ് ഓട്ടോമാറ്റിക്കലി എന്താവും, ഈ സ്പിറോഡൈറ്റ് ആയിട്ട് കൺവേർട്ട് ആവും. പേലൈറ്റ് ഫോം ചെയ്യും, അല്ലെങ്കിൽ ബേനൈറ്റ് ഫോം ചെയ്തത് കണ്ടോ, ബേനൈറ്റ് ഫോം ചെയ്തിട്ട് നമ്മൾ റൂം ടെമ്പറേച്ചർ ഇട്ട് പെട്ടെന്ന് കൊണ്ടുവന്നു. ബേനൈറ്റ് ഫോം ചെയ്ത് കഴിഞ്ഞാൽ പെട്ടെന്ന് തന്നെ റൂം ടെമ്പറേച്ചറിലേക്ക് കൊണ്ടുവന്നോളാം. അല്ലെങ്കിൽ പേലൈറ്റ് ഫോം ചെയ്താലും അതിനെ റൂം ടെമ്പറേച്ചറിലേക്ക് കൊണ്ടുവന്നോളാം. അല്ലെങ്കിൽ അതിൽ എന്തെങ്കിലും ഡിഫ്യൂഷൻ നടന്ന് വേറൊരു മൈക്രോസ്ട്രക്ചർ ഫോം ചെയ്യും. ഓക്കെ, ഈ പേലൈറ്റോ ബേനൈറ്റോ ഫോം ചെയ്ത് കഴിഞ്ഞാൽ പിന്നെ അതിന് റൂം ടെമ്പറേച്ചറിലേക്ക് നമ്മൾ കൊണ്ടുവരികയാണ് ചെയ്യുന്നത്. പക്ഷെ ഇത് ഇങ്ങനെ കൊണ്ടുവരാതെ പേലൈറ്റിന് ഇവിടെ തന്നെ ആ ഹൈ ടെമ്പറേച്ചർ തന്നെ മെയിൻറ്റെയിൻ ചെയ്ത് കഴിഞ്ഞാൽ എന്ത് സംഭവിക്കും, ഈ ഇങ്ങനെയുള്ള പ്രോബ്ലംസ് ഉണ്ടാവും. നെക്സ്റ്റ് ക്ലാസ്സിലേ എടുക്കാം. നിങ്ങൾക്ക് അടുത്ത ക്ലാസ് ഉണ്ടെന്ന് തോന്നുന്നു അല്ലേ? ഓക്കെ, നമുക്ക് ഫിനിഷ് ചെയ്യാം. ഓക്കെ, താങ്ക് യു. നമുക്ക് ഇനി എക്സാം കഴിഞ്ഞിട്ടല്ലേ, മൺഡേ അല്ലേ നിങ്ങൾക്ക് എക്സാം?
അതെ സർ.
ഓക്കെ, എനിക്കൊരു ഹാഫ് ആൻ അവർ എങ്കിലും കിട്ടിയായിരുന്നു ഞാൻ ഈ സംഭവം തീർത്താനെ. നിങ്ങളൊന്ന് പറ്റുമെന്ന് നോക്കാം. അങ്ങനെയാണ് എനിക്ക് ഇത് ഫിനിഷ് ചെയ്യാം. കാരണം ഇനി നിങ്ങളത് മറന്നു പോകും എക്സാം കഴിഞ്ഞ് കഴിയുമ്പോൾ.